Hello, this is my second lecture on metric space for third sem honors and DD students. I am RANJANA DUTTA from the Department of Mathematics, the Graduate School College for Women. Metric space. A non-empty set X along with the metric D defined on X is called a metric space. Thus, the metric space XD consists of two objects, a non-empty set X and a metric D defined on X. The element of X are called the points of the metric space XD. The set X is called the underlying set of the space and is generally used to represent the space. Now, bounded and unbounded metric space. Let Xd be a metric space. If there exists a positive real number k such that dxy is less than or equal to k for every point, every pair of xy in X, then Xd is that d of xy is less than or equal to k for every point of x and y in S, then Xd is said to be a bounded metric space. A metric space which is not bounded is called an unbounded metric space. Now, take an example. Prove that the mapping D R cross R to R defined by dxy is equal to 0 when x is equal to y and equal to 1 when x is not equal to I is a metric on R. By the definition D, we can show that the first postulate, second postulate, third postulate, and fourth postulates are satisfied. Now, we shall fourth postulate. Take the fourth postulate. If x is equal to z, then dxz is equal to 0. Since dxz, then dxz is equal to 0, and so d of xz is less than equal to d of xy plus d of yz. If x is not equal to z, then dxz is equal to y, and if y is any real number other than x and z, then x is not equal to y and y is not equal to z, then dxy is equal to 1 and d of yz is also equal to 1. So d of xz can be written as less than or equal to d of xy plus d of yz. Now for M5, if d is not equal to y, then by the definition dxy is equal to 1, which is greater than 0. Since the 5 postulates of a metric space are satisfied in R, so this function is, and it follows, it is a metric space in R. Now, take another example. Prove that the usual matrix space on R square defined in example 2 satisfied the required axioms. Here d is defined by dxy is equal to root of x1 minus y1 the whole square plus x2 minus y2 the whole square whole root. Since by definition dxy is a positive under root, therefore m1 is satisfied, m2 is also satisfied, because dxy can be written as x1 minus x1 the whole square plus x2 minus x2 the whole square. This is equal to 0. Hence, dxy can be also written as dyx. Hence, M3 is also satisfied. Now, to prove the M4, we take alpha 1 is equal to x1 minus y1 and alpha 2 is equal to x2 minus y2 and beta 1 as y1 minus z1 and beta 2 as y2 minus z2. Then dxy can be written as root of alpha 1 square plus alpha 2 square and dyz can be written as root of beta 1 square plus beta 2 square. Now dxz can be written as root of x1 minus z1 the whole square plus x2 minus z2 the whole square, which in the first case we add and subtract by y1 and in the second case we add and subtract it by y2 and we get ultimately alpha 1 plus beta 1 the whole square plus alpha 2 plus beta 2 the whole square. Hence we can prove that d of xz is less than or equal to d of xy plus d of yz. Now, alpha 1 plus beta 1 the whole square plus alpha 2 plus beta 2 the whole square is less than equal to root of alpha 1 square plus alpha 2 square plus root of beta 1 square plus beta 2 square, which further after further calculation we get 0 is less than equal to alpha 1 into beta 2 minus beta 1 into alpha 2 the whole square, which is a positive number, which is always true. Hence, M4 is also satisfied. Now, M5 is also obviously satisfied. Hence, D is a metric space. Now, take one homework and do it at home. Proof that the usual matrix on R square defined on example 3 satisfied the required axioms. So, thank you, student. Today, this much only.